Just start the recording. Cool. So as I was saying, on Friday, this coming Friday, we will have our first kind of answer key presentation session where I'll walk through the answers to the assignment due Thursday. I'd like to do that at noon because I have a medical appointment that I need to get to. So if that's okay with everybody, I'll do the answers at noon on Friday. And the due date for the assessment is Thursday at 5 p.m. So does anybody have any questions or anything like that? Seeing none? Okay. So today is kind of the introduction to the rest of the course. Beyond this particular chunk where I taught you about tidy tools and theories of tidy data, I'm not really going to be expecting you to learn very much new code at all. I am expecting you to learn a little bit about new statistical models, the first of which will be a generalized linear model, and the second of which will deal with some multi-level models. Justin asks, what format would I prefer for this submission? I'd prefer PDF, but if you can't get PDF, then I don't really care between HTML and doc. So, but just as long as you can get it to knit, it would be better to work with something that has knit rather than the raw markdown. Cool. So the getting back on the train. So the main kind of thing here is learning about statistical models, and in particular, I want you to get an appreciation for what people mean when they say statistical learning, as opposed to just sort of classical statistics. So to start this off today, I'd like to kind of give us a vocabulary that we'll use throughout the course. So the example in the reading from the James et al. Book is, generally speaking, you know, we might be attempting to predict income as some kind of function of, let's say, your years of education, number of years in education, and maybe your seniority. So the income that a worker gets is some function of these three variables, right? So what I think the statistical learning book does well is internalize the fact that all statistical learning problems are about, fundamentally speaking, making guesses. So if we had information on, you know, the number of years that someone was educated and the seniority in the company and their income, we might be able to construct a guess at maybe a new employee that's just been hired, or maybe we'd be able to infer the income of other colleagues. So the discussion in the James book would kind of lead us to model these things as there's some bit of information that we want to know. And that bit of information that we want to know, we might want to know it because it's hard to measure. We might want to know it because it's unreliable. We might want to know it because it's valuable. All these other reasons. But the point is, it's crackling a bit. Sorry about that. Sorry. Let me swap to a different pair of headphones because I think there's an issue. The whole recording. Awesome. How about now? Cool. Yep. Yeah, it was Mac sometimes has a bit of a problem with wireless headphones when you're not using their mic. Anyway, sorry about that. So what I was saying was, you know, the discussion in the James presents this kind of rationale for why we want to do statistical modeling. And I know that this may seem very basic to you guys, but it's important to kind of take it back to the very first point of why we're doing any of this at all, right? So this variable, this bit of data y, is usually something that's hard to measure, that's unreliable to measure, that we really, really need to know, that's valuable. And you know, there's varying terms that are used to describe this variable. I'll try and use outcome as the main word that I use to call y. Okay, so outcomes are the bits of information we generally want to know. And then in statistical learning, we have these sort of bits of information that we can collect, and we have information that we can't collect. And you know, we might have these as, you know, things that we directly measure. These might be digital byproducts. So like, you know, in a lot of companies, they use bits of information about your sort of metadata to try and serve you better advertisements. And their why is, you know, how likely are you to click on this particular advertisement? And then your kind of digital byproduct is something about your device, your location, your past browser history, stuff like that, that might allow them to predict better whether or not you'll click on an ad. Depressing example, I know, but that's where a lot of this thinking comes from. So you have the things that are hard to measure and that we want to predict as your outcome. And the things that we call our X's, we generally represent them as X's. These would be, in machine learning generally, we call them features, because they represent a feature about an observation, right? An individual or, you know, a place or something like that. Features is kind of confusing in a geographic context because in GIS, you're used to having a feature be like a geographical entity. So you've also been calling these things covariates. And then in machine learning, we have these errors, which reflect some kind of difference between the thing that we predict and the thing that we actually observe. And in statistics, we kind of call an instance of an error a residual when we actually have information on how big of the error we've made. Okay? So in statistical learning processes, this is kind of the model that you've seen before. And that's really kind of helpful when there's something that we really want to predict, or there's something that we need to know, or you know, there might be a concern about being able to guess about the value of something. All of those times when you're trying to either understand or guess or infer, all those things are what they call supervised learning. So supervised learning is one branch of machine learning. And that's usually, we say that you're doing supervised learning when you have an outcome that is modeled as some function of your input data and some error. In supervised learning, there's a right answer. So supervised learning is all about trying to predict or infer. Well, usually it's about predicting the structure or values of y, or it's about trying to infer the structure of the relationship between y and x. Okay? Sorry, I didn't mean to clear that. Jesus. Okay. This is one of the, Zoom has a lot better Blackboard function. So the way I'd like you to think about it is that supervised learning occurs when there's a y, when there's some right answer that you train your predictions on. So there's something that we know is true or something that we've measured to be correct, and we're trying to predict that, okay? Now, the reading talks a little bit about a measure that you've seen before. And it does this by reducing our model into two parts, right? So it says, okay, we might think about our error as being the difference between what we have seen and what we've predicted. Is everybody comfortable with that kind of hat notation there? So you would read that as error is equal to the y that we've observed minus the prediction that we've made for y. And in the James reading, what does y hat explicitly mean? Y hat explicitly means our guess for y. Anytime you see a hat, it means a guess. So if I write y hat, I mean I've put y into some magic box, possibly with other bits of information like x, and I've made a guess for y. Okay, that's all the hat means. Anytime you see a hat, it's a prediction, a guess. And that guess can be very sophisticated, or it can be very unsophisticated. All that is constructed from is f of x. So if you have done the reading, this is the discussion on page 19. So we can break this down, this difference in the predictions. Okay, I can't do that very easily. So I'm just going to redraw, turn that off. So we can break down the difference in predictions pretty easily. So we have our error is equal to what we've observed minus our guess. And that guess comes from our predictor function. So what the reading kind of takes you through is that you can break the squared error, which is generally the prediction error that we use in classical statistics. So it's this value squared. You can break that up into two parts, right? So if we recognize that the outcome, well, that's just our function plus the error. And this is just our function that we've guessed and our data. We have an incompatibility, right? So we have, just to help you define these things, this is the true relationship between our inputs, x, and our outputs, y. And it could be totally nonlinear, highly confusing, completely unknowable. And this is our model of that relationship. Okay, so those are two different things. And that's kind of the first important point to take away here. Anytime in supervised learning, there's going to be a true relationship between the things that are in your model and the things that you're trying to predict. Okay? That is kind of what we would call in statistics the data generating process. Okay? So the exact representation, this true relation between x and y, is like the real model. We don't know what that is. So we're going to fit some other model of a relationship between x and y that we think, is reasonable. Throughout your time in Bristol, we've used a linear regression normally to make this model. So what that means is that we would never really think that the true, real process is a linear relationship between x and y. But we might think, okay, by using a linear relationship, we can get good enough predictions. The true relationship could be nonlinear. It could have additional information that we don't have access to. So you can think of the difference between f and hat f as what we would call specification error. It means you've picked the wrong function to relate the inputs to your outputs. And because we can't usually know the underlying true f, the real relationship between x and y, it's highly likely that every time we fit a model, we will induce what's called specification error. The reading and sort of machine learning in general calls this reducible error. So they call the difference between the true relationship and our model of that relationship as a reducible error. That's because we could pick a better model, and that might give us a little bit better of a structure towards the true relationship between x and y. So we could always use a little bit more, qualitative research or knowledge of the problem to come up with a better f, a better function relating x and y. And that's why the reading calls this reducible error. But you can also think of it as error in the specification of your model. It's error in the functional form that you choose to model the relationship between x and y. Okay? So, going back to this thing where we have error squared is equal to, we have now function of x plus the unknown error term minus our guess at the function and the data that we've trained it on. Okay? So again, this is the true value of y. So I can write that in for you here as y. And this is our guess about y, having assumed a model form. Okay? And the book talks about how if we rearrange these terms, we can get the difference between f of x and our guess at the functional form. I don't know why it keeps on making that straight. So we can rearrange it into one component that's about the difference between those two squared, and then another component that's the variance of our error. Does that make sense? Well, actually, we should use an R to represent this. So this is the residual. So that should be R squared. So the reading will discuss this in that you have your kind of reducible specification error, and then you have the irreducible, sometimes called intrinsic error. So in statistical learning, we're always kind of making a trade-off between the things that we can deal with in the reproducible error. We're trying to find a better specification, and we might choose simpler specifications so that they're easier to work with, or we might choose more complicated specifications that better reproduce the data. But at some point, there's going to be error in the process that we can't remove. So our predictions are always going to have these two components. Now, this gets important when we're talking about data that is in sample and data that is out of sample, right? So if we pick a very, very complicated function here, make this reproducible error as small as possible. We pick some really complicated guess for f hat of x. And we make it so that there's basically no error in predicting y. That model actually might not be very good at predicting new information. This process, by which you pick way, way, way too complicated of a form of f, is usually known as overfitting. Overfitting occurs when you have too much complexity in your f or your x. And I'll give you a little example of this now, okay? I'm going to leave this up for a second so that people can copy it down and ask a few questions. But I'll give you an example of why it matters that we can think about this in a second. Finn, so that happens because of the way that when you actually separate out these terms, you're going to get cross products between the predictions and the errors. So the variance of the error is going to depend on the functional relationship between the error term and the model you specify. Usually we just assume that's it's unrelated, so you just get something that's like e squared. But it's not always the case that, oh shit, I didn't mean to do that. Yeah, I'm not a big fan of the blackboard, whiteboard. But that's why. Normally it's just a proportional to your squared residual. But there's always a trade-off between your residual, because your residual contains both reducible and unreducible error. So there's no way for you to know what the unreducible error is in abstract. Okay, so let's do kind of a very simple thought experiment, right? Statistics is about guessing. And if there's one thing that you take from this course, it's that data science treats statistics as much more of a guessing game than anything else. So imagine we were flipping a coin and we tried to, record the heads or the tails of that coin using ones or zeros. Okay. And I told you that I asked two different people to come up with a guess for what the next outcome would be. So this is a supervised learning problem, because you know immediately that there's an outcome that you're trying to guess, right? Okay. So one form of our estimator, and our x, there's no relevant information about the coin. One really easy estimator is to say that the coin always is tails, meaning it's always 0. That's one estimator. I could just say, this coin is biased in such a way that it's always going to be tails. I could also say, okay, a different predictor might be, what was the last 3 flip? What was the most common? In the last flips? Pick the opposite. Does anybody else have any ideas about what a good estimator might be? So some people might think opposite of the previous flip. Great suggestion, Anna. See how many times it's been flipped and then how many times it's landed on each? Well, that gives us an estimator, Willow. That can tell us, which side is more likely given what's happened, but that doesn't give us an information on what to guess for the next one. We could guess which has been the most common, which I think is what you mean. So let's do that. Okay. So if we do this, the first estimator, the first functional form, has a pretty good score. It gets 5 out of 9 flips right. If we use the second estimator, what was the most common in the last 3 flips, pick the opposite, it would get, well, let's say that it picks randomly in the first one, so we don't know what it would get there. But it would pick the opposite of 1, it would be 0, And between 0 and 1, it would again be random, so let's give it a 0.5. So we would call this 2. Now the most common here is 1, so it would pick 0. The most common here is 0, so it would pick 1. So we're at a score of 3 now. The most common here is 0, so it would pick 1, fails again. Most common here is 0, it would pick 1, fails again. Most common here is 0, picks 1, and it gets it right. Most common is here 0, and it gets 1, gets it right again. So we have something about 4 to 5 right. Oh, fuck. We would have something about 4 to 5 right if we did that rule, which this one was just pick 0. This one was last 3. This one was opposite last 1. Sorry, the Blackboard Collaborate Ultra Blackboard is just not as good as Zoom. And then this one was most common. And the sequence was 1, 0, 1, 0. No. 1, 0, 1, 1, 0, 0, 0, 1, 1. I think it was something like that. And this one was 5 out of 9. This one was, let's say, 4 out of 9. The opposite, the last flip, would be we don't know what it is in the 1, and then it gets an answer for 1, 2, gets that one wrong, gets that one right, wrong, wrong, right, wrong. So that's again about 4 out of 9. 1, 2, 3, 4. And then the most common flip is 0, so it would miss, well, it was 0, but now it's even. Anyway, the most common flip misses all the ones that it isn't, right? So it might be 5 or 4 out of 9. God, I'm kind of annoyed that that deleted itself. But the point is, the point of this example, which I'm frustrated that the Blackboard erased, I'm sorry about that. The point of this example is to show all of these different things are just estimators. They're just way that we're going to guess the outcome of a problem. And so most of the time in your linear regression fashion, we've picked a very simple linear relationship between variables. But data science is the kind of realization that that model, even though it may be good, isn't the only kind, right? This down here, pick the most common category, is a pretty reasonable way to predict things. But you could make arguments about all these other things, right? If you had good belief to say that the coin was biased, then just picking 0 in the long run might give you a better set of guesses than picking the most common, which might flip between 0 and 1 depending on random noise. So the kind of ideas that are behind this is just that, you know, when I ask you about how to guess, or in the future assignments, I might ask you, what's your best guess for X or for Y or for this value or that value? I'm asking you literally to use your intuition, you know? If I'm asking you to make a guess given some data, then it's just using these kinds of different ways of constructing a guess. And as long as you defend how you're going to make that guess, you'll come out okay. So the point of this example then is to show that there's a bunch of reasonable estimators that you can pick. All of these are pretty reasonable. Some of them may be more different than others, and just because it's a simple algorithm doesn't mean it has bad performance. Just pick 0 could be a really, really, really great model for rare events. You know, if there's some kind of process where, you know, it's extremely unlikely for something to happen, then a really good estimator is nothing happens ever. In continuous data, we've talked about functional forms that follow along lines, right? So we might say we have something like this. And we just have an x and a y. And so most of the time in our classes in Bristol, we've talked about linear regression, right? And you might find a line of best fit using linear regression like this. And we've spent a lot of time interpreting things like the intercept and things like the slope, which I would generally call parameters. And parameters are just things that model the relationship between x and y. If you pick a functional form, like a line, then you need two parameters, an intercept and a slope, or a gradient, as you might say. But that's not the only prediction that's possible, right? So another prediction type might be something, if you have read throughout chapter 2, you've seen something called a k-nearest neighbor algorithm. And that's an extremely fancy way of saying average the guesses that are close by. Okay? So a k-nearest neighbor line, let's fit that to the data. Very simple to construct. If I start at x equals 0, what's the closest value of y that I've observed, not on the line? Well, this observation here has this value of x, let's call it x1, and this value of y, let's call it y1. Therefore, a reasonable value for the k-nearest neighbor prediction is just to say, okay, if I'm closest to this first point, then my prediction is that point's value. So my KNN regression line is just going to be flat until it hits that point. And it's going to be flat until it gets halfway between that point and the next point. And then it's going to jump up till it's at y2, and then going to go straight until it finds the next point, and then jump up to that value of y3. And then when it sees the next point is down, it's going to go down over to that point, and so on and so on. Exactly, Hannah. This is if k equals 1. So I get something that's zigzagged like this. As a k-nearest neighbor prediction of my line. Does everybody see that, how that works? The KNN algorithm, as it's called, the k-nearest neighbor algorithm, just tries to make predictions based on the closest data that you have. This works in multiple dimensions as well as in 2 dimensions. So if I have 18 different variables and I'm trying to make a prediction about y, I just give exactly the value of y that's closest to that point, if k is 1. You can see that this is a very squiggly line, right? Extremely squiggly. Now, another type of prediction that we've talked about. Well, before I move on to a nonlinear model, let's just say, now if I wanted to do k equals 2, what about outliers with k and n? Great question, I'll get there in a second. So in a KNN model, we're always constructing our prediction about what our outcome is going to be based on some number of closest input points. If I have more than one, so here I'll write it down on here, this is KNN 1, and this is a linear model. If I have more than one nearest neighbor, I might have something that looks like this. So I start off my prediction just like before, and then at some point, I might see both of these points here. So once I see both those points, my line goes up to their average. And then once I see my new point that's up there, it goes up further. Once I see this other point, it might go down a little bit, and then it might go up as it sees more points, and then it might go up as it sees more points. But the same idea is that at this position of the line, it's taking the average of these three nearest points for its prediction. At this position of the line, it's taking the average of this point, and that point. At this position of the line, it's taking the average of this point, that point, and that point. And it might squiggle and then go way up and then fit like that. So that kind of model is less squiggly than the blue. It's smoother. It's not jumping all over the place. So the blue line might be what's called overfit. It's too jumpy. It's too responsive. KNN3 is a bit smoother. In practice, we can tune this using that in-sample and out-of-sample data. If I observe new points, and let's say, they are here, and maybe here, and here, and here. The linear regression, despite the fact that it's the least wiggly and has the most errors in the set of points we observe, it might actually be better at constructing out-of-sample estimates. Does that make sense to everybody? All we're doing is coming up with a way to predict the data that we need. And if our prediction regime is give us the best guess for all of the red points, then a KNN algorithm can do pretty well at that. In fact, it can do it perfectly. But, as Sophie asks, if we observe new data, like the green dots, KNN algorithm might not actually give us good estimates of those. So the KNN algorithm fits really well to the red dots, but might fit poorly if we take new samples and get the green dots. Typically, this trade-off is called overfitting. As I said before, the KNN model has only one parameter, which is the number of nearest neighbors. The linear model has two parameters, which is the slope and the intercept. So the whole point of statistical thinking and sort of this statistical learning is to get you out of thinking about the linear model as this concept that we teach in statistics because it's super important for life, and more about thinking in terms of guessing. A linear model is a really smooth and simple way to make guesses about data. Other kinds of approaches, like a k-nearest method, give me the value of the most similar thing to what I've seen before, they're valid ways of learning too. And data science and statistical learning generally is the realization that it's not all about linear models. It's also about thinking about the guesses and how guesses are made. Now, it's a funny thing for me to say this and then just to give you 4 weeks of linear modeling training. But if there's one realization that I'd like to think about, it's that linear models, no matter what form or how they come, are just ways of summarizing the data in this fashion. They're just ways of making guesses. And they're deeply and directly connected to the same kind of logic that the KNN is. They're just picking the best guess given the data they've got. And KNN says, if all I can see is this one point on the horizon, I'm going to guess exactly that value. Does that make sense to everybody? Has everybody followed this kind of discussion of the squigglier lines and then the slightly smoother lines and then the linear regression as being a trade-off between something that listens to the data way too much and something that is a bit less sensitive to the data? This is kind of the main concept that's in statistical learning chapter in section 2. You have to think about accuracy both in terms of the data that you currently have, the red dots in the figure, and in terms of the green dots, things that you haven't yet observed but might in the future. And it could be that some algorithms are really, really good at predicting the red points, the things we've seen before, but they might actually be very bad at out of sample accuracy, which are the green points that I've drawn on the map. Data science specifically, why would we want to predict what we have seen before? Well, anytime you've used a regression, you've thought about the R squared, right? Every regression has this R squared value. R squared is an in-sample accuracy measure. It tells you the accuracy of the points that you've seen. In statistics, we've focused on this because the kind of classical way of doing statistics has minimized the amount of data that you need to do, because data collection is generally expensive, right? Before computers, other kinds of things, statisticians were interested in minimizing the amount of data that you had to get a result. So in the classical perspective of statistics, you're trying to get the best squared you can for the data that you've got. You've done a lot of design and training ahead of time to make it so that the data that you have is really lean. I've constructed this really complicated survey, and then I'm just interested in optimizing the sample R squared. Further, there's arguments in geography specifically that say we don't really have out-of-sample data. You know, if I study depression in Bristol, I've got all the LSOAs. So all I really need to worry about is predicting the deprivation in those LSOAs. If I have all that data, I should use it. So there's a really good kind of reason to do that. It's that, you know, it might be the point that you're doing. Emily, supervised learning is learning about a function when, can someone be able to control that? Supervised learning is learning when there's a right answer. So supervised learning is just trying to predict something where you know the right answer for some points. In this example, we're using supervised learning because we're trying to predict the values at the red points. I wanted to get to unsupervised learning. The two kind of whiteboard wipes have inhibited that. Broadly speaking, unsupervised learning is the contrast to supervised learning. In unsupervised learning, you're just looking for structure in the data. In that case, you might have a bunch of different variables, but you have no why. You have no outcome. And all you're trying to do is describe structure in that data. So to quickly show you what that looked like, it's a common kind of thing in unsupervised learning. Say you have education and you have income. You might have a bunch of people that are low paid and haven't really been in school a lot. Supervised learning has testing data. In unsupervised learning, there's no specific test. So you might have a collection of people in this sort of relationship between education that are not very educated and don't make a lot of money. And then you might have a whole other group of people that make a lot of money and maybe also don't really have a lot of education. These might be like entrepreneurs or people like that, maybe never got formal education. And then you might have students that, they get a bachelor's degree and they find something in their field, and they're usually more well off than the rest, but maybe there are some that, don't get jobs in the areas that they like, the areas they studied for. You might have graduate students who are very well educated and make next to nothing during their times. And then you might have observations all the way up here that are highly educated, highly paid individuals. When you see this in a table, all you get is a value of income and a value of education. And what unsupervised learning does is it tries to say, okay, this broadly speaking is one type of individual. And maybe this is another type of individual. And this is another type of individual. This, I can't really tell apart because they're touching one another. So this might be a detected cluster, but it might actually be wrong from a sort of theoretical perspective. The point of unsupervised learning is all of these points have no explicit label. You wouldn't really know what type these things are until I get an algorithm that says, oh, this is a type 3 person. This is a type 4 error. So classification is a common thing in unsupervised learning. You're just looking at this kind of structure in your data. So again, the kind of division between supervised learning has a right answer. It's why that you're trying to predict. Unsupervised learning doesn't really have a right answer. There are ways to justify the answer, but you're seeking structure in a way where there's not actually a known structure. Okay? So that's the division between the two. As Becker has suggested, supervised learning has data, whereas unsupervised learning basically does not. You're just trying to make the best of them. So the main concepts I want to get to today were the supervised versus unsupervised distinction. I wanted to talk a little bit about partitioning of error into the reducible and irreducible errors. I wanted to talk a little bit to show how you can pick different functional forms for predictors, and that we did in the coin experiment. And then I showed you different ways of fitting a line. I showed you the linear regression and a KNN. Going forward, we're going to be talking a bit about how to make predictions for binary outcomes. So that's what this next chunk is about, this concept of things called a general linear model. And those predict things that are not necessarily normally distributed. So they're rules for making predictions when you don't have normally distributed data, when your data is not necessarily continuous. Okay? So I have to hop off for another meeting. But I hope that this was informative and at least the discussion was useful. I'm sorry I'm still getting used to Zoom. I'll be getting used to the Zoom Blackboard because definitely not as good as the other tech. But I hope to kind of get a mastery of it good enough that I can continue doing this. Patrick asks, could I please check which dates the assignments will be done in the future? Yeah, they're all on my website at ljwolf.org/teaching/GDS. Those should all be current, and your submission date for the first assignment should be open now, and it's due on Thursday at 5 p.m. Sound good, guys? This is a very fundamental part of the first part of the course. So it'll all be kind of thinking about statistics rather than about programming and stuff like that. So we'll join next time for a little bit more on fitting code and thinking about the workbook that I've posted online. I hope you have a great day, and I look forward to seeing you soon. Bye-bye.